Okay, so whenever you non-dimensionalize, it's good to just match, right? It's pretty natural, and I think I always support sort of the artistic nature of just trying to figure these things out. So if you're trying to write a non-dimensional coordinate x, I use this notation of star. Some people will use a dash. Other people may use like a tilde. I don't usually see that one, but I like the star notation. So, and what it means is you have your sort of dimensional x coordinate, and you're normalizing it by that L value. So it makes pretty much, it's okay, right? This is units of meters over meters, right? It's pretty intuitive of why you'd even pick this one, because in this situation, right, I'm measuring some x coordinate, and this was the L. So I'm really it's okay for me to normalize this x coordinate by this measured equilibrium distance. Right? So kind of a different way to say this in scaling is sometimes you can just say, well, x scales like L. You say that the x coordinate dimensionally is kind of going to hang around this equilibrium length. It's the assumption that you have of the dynamics, but it's a rational one. So kind of these two things mean the same thing. You tell me this. If you tell me this, I immediately can go to that in my head. If you tell me this, I can immediately go to this in my head. So either scaling or non-dimensional, they will mean the same thing. I usually write out these things before I do something like that. So for the whole system, we had all those parameters. And what you non-dimensionalize are the variables. So this is a fairly simple one. Right? Right? You want to turn this into a differential equation involving x, non-dimensional x's, and non-dimensional time. Only do the variables. We don't non-dimensionalize the parameters. They're going to tell us about them. So, well, what did the time scale like? Usually go for a tau. So what's the time constant of this? Say you actually don't know it though. So that's really kind of that's where the scaling and non-dimensionalization have an interplay together with. So we don't actually know what the time scale is for this differential equation. We can figure it out by at least subbing in this L term here. So if you don't remember what the dots are, it's just this, right, d by dt. So I'm just simply going to then sub in, right, this, right, remember this equation right here, I'm just going to sub that in. So, right, this is equivalent to saying L times. So you take this, sub it in here, sub it in there, right? Nothing too crazy happens after that, but we also want to sub in the time because it pops in these differential things. So again, we don't know it, but we say something like that. This is equivalent to the same process. Dimensional time is equal to my time constant times my non-dimensional time. So subbing those into here, we'll get these square relationships. Okay, this one now is a tau squared. There's a tau. So now we have the non-dimensional equation, where right now these are all non-dimensional terms. And that's important, that the differential parts of these equations are non-dimensional, and we also say that they're order 1, or they basically look like the number 1, because all the values of x, right, all the values of x were around L, and all the values of time are around t. So again with this, if this non-dimensional x varies around a lot, that means that this quantity right here is varying, but all these terms are hanging around L. So this, right, you're saying that the x looks like 1. And that helps for these other substitutions later. Okay, so that's good at those. And now we can kind of just look at this in terms as a function of the parameters involved to the equation, which is good. That's kind of the goal of this scaling stuff, right? The whole point of this scaling of just non-dimensionalizing your variables and then trying to see what terms matter, we haven't even done that yet, but the idea is you turn differential equations for the variables, right? You turn the differential equation in terms of variables into an algebraic equation for the parameters. So hard, easy. Algebra is easier than differential equations, so we want to be here. So all this non-dimensionalization got us to a point where we could make the differential operators or the differential terms in our equation have a bunch of stars on them, right? So we got to, right? And then still actually haven't done scaling yet, but we're getting around to it. So this is just the non-dimensional equation. I haven't written any twiddly lines yet, but we're going to get there, right? Because the whole thing is these numbers right here now are basically 1. This scales like 1, this scales like 1. So it's an order 1 term. So now you kind of go into this scaling world where you say, well, this parameter, go comma, this parameter scales this parameter. You never say that something scales 0 for some reason, for other reasons, but that doesn't really matter. The whole point is you have to compare things. So this equals 0. You move this over to the right-hand side. But this term right here doesn't care about positive or negative or algebraic signs. That's why you even have these comma things right here. And now you can talk about the order of importance of the parameters. Remember that we know and can measure, right? Known, known, known. The L was known, but it didn't matter. Right? These we know. Right? And the whole point is we're trying to figure out, right? Trying to find the time scale. Trying to find, what does this happen over days? Does this happen over minutes? Does this happen over nanoseconds? That's what asking this question means. So you can think of this as one equation and one unknown, but scaling really works if it's only comparing 2 terms. So these are sort of the measured things. And then you can now do some cases because I knew what M was, B, and K. Right, so this is one, right? If this B value, we're just going to say is just an enormously small number. The damping of the spring is just horrible, right? You can neglect that one, and then you get this relationship, which tells you that the time constant of the time constant of this mass spring damper is what? Right? If you all recognize that, right? It's like the frequency of the system, right? You can just do it for just the parameters and non-dimensionalizing the equation. So this, if there's barely any damping in there, the time will look like this. Likewise, you could have, what if I just know that I just have some puny spring involved in this system? Now you have this time constant. So again, these are right. This is an expression of known things, so it can tell you sort of the time rate of what that differential equation is going off of. The other one we have is what if it's extremely light. And you can also have the other way too. You could actually comparatively say that, like, well, right, what if I just know that this number is way, way bigger than the other one? Like, these two numbers are giant, while this one is like 1. Same idea. And then, so right, then this one would be and there's another time constant. So it's really fun. Take a differential equation that is physical, has dimensions to it. You make the whole differential equation non-dimensional. Then you get some expression in terms of scales, right? You get this expression of like a differential term that's just like behaves like the number 1, and then a function of these parameter terms on the end. And then you just make rationalizations based on the numbers that you know about. So I think it's pretty fun. And I just wanted to give that briefing because to get these boundary layer equations, it relies heavily on this whole scales concept of figuring out what the delta is. See how before we figured out what the time scale was based on parameters? For the boundary layer, we're going to figure out what this value scales like using the same techniques. That's just an example of how you can do this for any sort of physical differential equation you have. So I have some extra credits in the notes for you to do that yourself. I think it's really, really fun. One of the best ones to do it is just take like the one-dimensional Navier-Stokes equation. Say just like this equation, right? So now, a great way is just like do all the 2x2 comparisons to figure out the velocity scale or time scale. And that's just the fun for yourself to just kind of like pick 2 and compare, right? Pick 2 and compare. And then you can figure out actually all these time scales and actually calculate some fluids involved and see like what the order is on this time scale. So what I mean is like figure out, I did three cases for 3 time scales. Do like 1, 2, 3, and do those 3. So, and you can do more too. You could even do time scales where it's like, you can even do time scales where you balance these 2 and you say these 2 balance. So that's 2 equations and 2 unknowns. You can just go totally deep in this stuff, and I think it's super fun. But those are in the notes for those extra credit problems. So now we're going to actually get to the boundary layer, but that's just a sort of mathematical example of how you use this little tilde symbol to throw away terms.